in this second part of the lecture, we see how we use the reducer index function we have just implemented to implement the head reduction, to implement the normal remainder, which takes care only of dividing the head of the polynomial, leaving out of what happens in the tail. So we concentrate on the leading power product of the polynomial f. So we start implementing this function. Indeed, this is already the refined version, and then we will see, sorry about this, what happens if we introduce some buts. So how does it work? It is essentially as the Euclidean division that you saw in previous lecture. So what do? We first of all, we define R as f, our starting point, and then we repeat this process. So we look at the reducer index, and what happens that this polynomial at some point might become 0, the remainder, or it might happen that there is no other possible division, and that is why we wanted to intersect with the returning 0 if there is no possible division to do, so that here we check after the call of reducer index if the index coming out is 0. That means no more division. If there is no more division, then whatever happened r equals 0 or are not divisible by any of the polynomials in the list, we return r, the last remainder we got. Okay, we skip these 3 lines for a moment and we go on with the algorithm. So what do? So we found if we are at this point, it means that j is not 0. There is a reducer, a possible reducer for our polynomial f. Then we compute m, the leading monomial, which I remind you contains the leading power product and the leading coefficient of my polynomial r, the running remainder r. And we divide this by the leading monomial of the of Lj, the jth element in the list L. Then the remainder, as we did in the computation by hand we did before, the remainder is now defined by R minus M multiplied Lj. Then we have killed the leading power product and we go at the top again and look if there is a new reducer for this new remainder. If so, we keep dividing. If not so, we have j equals 0 and we return the remainder as is. So let's try this function. So there's one different thing from before. Okay, I did an error. I knew that I was making some. Okay. I guess I didn't select it properly. We have no return at the end. You see, here we found that without this return at the end, we get an error saying that the function must return something. And here it seems that we forgot to do it, but we haven't, because we are in a repeat and repeat loop that goes on forever. So there is no way to get out of this repeat if not by this line, by the returning function, the returning value. So let's try on the examples before, the division by G1 and G2, and we get the same result as we did by hand, and the same result that we get with CoCoA. and then the normal remainder by G2 and G1, looking at G1 when in the reducer index function before looking at G2. Here we see that this is not a full reduction because we have x squared, and I recall that G2, if I recall well, it could divide this monomial inside of the tail of the polynomial. But as I said, now we are writing normal remainder LPP, that is the head reduction. We'll just look at the head because in the computations we're going to do, that is the only crucial part. Now I show you what this line means. If verbosity level bigger or equal to 9, then print something. So what happens if we put the verbosity level to 9? We get all this information on how many operations we did. And so we will see with bigger examples soon, next lecture, how big the divisions can get. And then we are very grateful to CoCoA that it does the division instead of having us to do it by hand. And this is what happens when we do the division the other way. We have the reducer index, you see 1 is preferred, so 1, 1, 1, 2, and then 1 again. And here, remember that in this case, the first one is G2 and then G1. So we look at G2 first. G2 divides these two leading power products and not the third one. And so we have to take G1, which is the second in my list. And we get two different normal remainders. So this is very interesting. This is very interesting because when we develop an algorithm, it is very useful to know what's happening inside. Because when we want to optimize it, to make it faster, or to understand why it is so slow, or to understand what kind of computation goes inside our algorithm, then it is nice to have this printing information. And it is very convenient, this technique that we have in CoCoA of the setting a verbosity level. So you can have different informations printed at different levels. So if you want CoCoA to be completely silent, then you set the verbosity level to 0. If you want it to be very verbose, you put a very high number. And if you want to have something in between, you choose your own levels. Technical information in CoCoA, the internal functions of CoCoA, which have verbosity implemented in, start from level 10. So we reserved for the user the levels from 1 to 9, so that you are sure that at that level you are not going to have any informations from CoCoA which is not what you implemented. So apart from knowing what's happening inside your algorithm, this is a crucial information to use when you are debugging. So what happened? For example, I show you a buggy version of our function. So I read this function, looks very much like the one I did before, not very clear what's wrong. No, I indicated it here, but this is a very common mistake, very common. So instead of having R gets R minus the product of M and Lj, I have F. So it's very common to get a letter wrong. So what happens if we run this algorithm? We set the verbosity to 0. We start function, and we say, oh boy, this computation is very heavy, must be very complicated. And then you remember that this was the computation you did by hand. So you say, there's something wrong here. So I stop the computation with Control-C. Control-C. I pressed the wrong button. Control-C, Control-C. Okay, here it stopped. So here it says that it stopped while it was reading this line. It's not very informative when you interrupt CoCoA, really, what the line that it gives you. So we restart the computation with verbosity level 9. And we started, and oh boy, we see that it is in an infinite loop. And we also notice one thing, that is essentially swapping between two values. So you understand here very clearly, I stop it, Control-C, Control-C. It is very clear that the bug was indeed in the update of my R. So R is wrong. It means that I did the wrong computation defining R in the loop. And so I can go there and fix it. Let's see another buggy version. This is another buggy version. Okay, I executed it. Yes, it read it without giving errors. So what is the wrong thing I did in this buggy version? Instead of returning R here in the loop, detecting that there is no possible divisor, I put return R out of this repeat and repeat loop, which never ends. So this is another very common bug when you write code. So to put the return in the wrong place. So what happens? If I have verbosity 20, I run my function and it says that index 0 is not in the range, and 1 or 2. That means that I'm trying to look allow 0, which is not a possible index in CoCoA-5. And when this happens, you get very puzzled because you say, how do I get index 0? Because you think of G1 and G2 and F as they are at the beginning of the computation. So you know that G1 divides F. So you start thinking that there is a bug in the function reducer index, because it shouldn't give 0. You know, it divides. This is very common because when you find a bug, immediately you get convinced that the bug must be somewhere, and you start chasing the bug in the wrong place. So we use now our verbose version. So we run it, and indeed we see that the computation was right. In fact, it started dividing. So the problem is not in reducer index. That works perfectly well. The problem is that at some point, the reducer index is 0, and I'm not intercepting that inside of the loop. And so we go and check why it is not getting out at this point where it should get out. And we put the return statement in the right place. So these are two common errors, and I really do suggest you to put printing in your functions. So printing is useful for understanding how your function works, but is even more useful to understand where the bugs are, because we all put bugs in our code. And then I leave you with a few exercises to do, depending on what your preference is, on how deep you want into your knowledge with CoCoA. So the first exercise is very hard to do. You have to invent errors and try to see how to find them. And I learn to see what kind of message CoCoA gives you so that you get used to error messages and what might go wrong when you implement something which is not perfect. Then the second exercise is to implement the full reduction. That means we have implemented the normal remainder LPP, which just reduces the leading term, the leading power product of F. Write a new function normal remainder, which implements the full reduction. That means, I give you a hint, you call normal remainder until you can divide the LPP of R. When you cannot divide anymore the LPP of R, then you put aside the LPP and then recompute the division on R minus the leading monomial. And then you sum all these monomials and get the the remainder of the full reduction as the NR function in CoCoA-5. Then there is an easy exercise if you know the theory. If not, it's nice to experiment with this. Find 4 interesting examples of F1, G1, and G2, such the remainder by G1 and G2 is 0, which means that F is in the ideal generated by G1 and G2. But the remainder with respect to G2 and G1 is not 0, so that division would give you really no information about F belonging to the ideal or not. So if you know the theory, you know how to find these examples. If you don't know the theory, it is a nice challenge. Then, if you're a very expert and you know what the Janet division is and the Pomaré division is, you can experiment and you implement your version of these 2 divisions, which are sophisticated versions of the division algorithm. Okay, enjoy CoCoA. Over for now.